In this video, we start our module on quantum machine learning. We will be using the quantum algorithms that we have developed in module 1 of quantum computing and use them on machine learning algorithms to obtain faster quantum machine learning algorithms. In this module, we will cover quantum versions of the following machine learning algorithms: SVM, support vector machine and kernel methods, principal component analysis for feature extraction, k nearest neighbor, variational methods, variational circuits, and quantum versions of them, which will then provide us auto encoders, kernel methods, and neural networks. So as we mentioned earlier, in last module, we discussed many quantum algorithms. Most of these algorithms provide exponential speedups over the classical algorithms, and we are going to use this quantum algorithms on machine learning algorithms to provide faster algorithms. Some of these algorithms are going to be what is called hybrid algorithms. That is, part of it will be quantum algorithms and the other will be classical algorithms. In each of the cases, we will first provide the classical machine learning algorithm and then its quantum hybrid version. So we'll work in the following framework in most of this video. This is supervised machine learning framework, although we will also talk about a little bit on the unsupervised case. In the supervised case, we start with your training data x1, y1 to xn, yn. So n data is samples. Xi are the observations, maybe images and so on, which forms a vector in Rm. And yi are the corresponding labels. So if xi's are the images, yi may be the objects that are given in image xi. Starting with this training data, we train the machines, and which is called machine learning. And two traditional methods, problems in machine learning are classification, where the yi, the samples belong to a finite class, which will denote from yi belonging to 1 to m. The other problem is the regression problem, where yi may actually take values in real vectors. Rm prime. The dimension of yi may be different from that of xi. And in this case, yi's are related to xi's via this relationship where yi is equal to m naught xi plus zi, where zi is noise with the expected value 0, and xi and zi are independent of each other. In this, m naught is an unknown, possibly nonlinear function, which we would like to estimate from the observations x1, y1 to xn, yn. So how we train the machines based on this training sample? We define an empirical loss that is given as 1 by n sigma I is equal to 1 to n L H I Y I, where L is a loss function, which we will explain and depends on the application we are addressing, and H are some functions will belong to this capital H. We call it hypothesis space. Given Xi, and if we choose H will assign Xi a label, which may or may not be same as the given label Yi in the training sequence. And then for a given H, we find the loss if we choose H between Hxi and Yi and take the average of the loss, and we train the machine so that the H finally we get is minimizes this empirical loss. For classification problem, L is equal to 0 if the class H given by h to xi is same as that of xi, yi. So if hxi is equal to yi, then loss is 0, otherwise it is 1. In case of regression, L is for a given h and xi, hxi minus yi whole square. I mean, these are two possible things. There are other variants, but these are among the most popular loss functions. The first method we talk about is support vector machine. Support vector machine is for classification problem. In fact, it's initially designed for binary classification where yi belongs to -1 or 1. And any hypothesis h given an observation x will be defined at hx equal to sine of inner product between w and x. Remember, x is a vector, and then w will be of the same dimension as x plus b. B is some constant. Fixing w and b, this quantity inside the bracket, makes a linear function. And if we equate this to equal to 0, then that will be a hyperplane in the vector space of x. Sine function is sine of z equal to 1 if z is equal to 0 and equal to -1 if z is less than 0. So therefore, this quantity, which we have defined as hx for given w and b, gives the value either +1 or -1, and this is how we interpret the class given to x by this function h, and h has been specified wb. Take this example in this figure. If x has two components, x1 and x2, and we have plotted them here, these blue dots correspond to class 1, and red dots will correspond to class -1. And these lines that you see here, they correspond to the different hyperplanes. Choosing different w and v, we'll get these different lines. Choosing any one of these lines classifies these points into two classes: the points above the line and the points below the line. So this will correspond to when the corresponding this hx has value +1, and this will correspond to when it has value -1. So as you can see here, for this data, we can have different hyperplanes corresponding to different w and b, which classify these points in the training sequence correctly. That happens if the training sequence is linearly separable, in the sense that there is at least one hyperplane which will correctly classify all the training sequence. Of course, there can be cases where the data is not linearly separable, and we'll discuss about it later. So suppose data is linearly separable, then we want to find a hyperplane H which will classify the data correctly. But then there may be multiple such hyperplanes, as 3 hyperplanes we have shown here. And then the question is, which one of these one should pick? For the same data, this hyperplane that is given here is considered the optimal or best hyperplane, or the W and B corresponding to this hyper. Why it is called that way is because the points here in this class and the points here in this class are not only getting correctly classified, but the nearest points here of this class and of this class from the hyperplane are at the maximum possible distance among all the hyperplanes which separate these two classes properly. How to get this best separate plane? And of course, one can ask why it is called the best, because intuitively it looks like if you pick this among all possible hyperplanes which classify correctly, in future or generalization error that you will obtain corresponding to this will be minimum, because the noisy sample or general sample from this class may be coming closer to this, or maybe even crossing it in some cases. Similarly here, they may be crossing it, and this is the line which will give minimum error in the generalization case once the perturbations of these training sequences are there. Now, how to get this best separating place is by solving this equation. Remember, we want to get W and B. W is the vector and B is a scalar. If you take half norm of W square plus gamma, a positive constant, norm of theta with respect to L1, and this is with respect to L2. And this is subject to yi, remember the label corresponding to xi, into inner product of wxi plus b is equal to 1 minus zeta I are greater than equal to 0. So if you take this, solve this optimization problem, this not only will provide the best separating plane, hyperplane, in case the data is linearly separable, but it is in some sense a more general case where some points may not be properly, may be, so overall the data is not perfectly linearly separable. And in that case, also it will provide a hyperplane which will perform well if we solve this system of equations. This optimization problem is convex optimization problems. Therefore, it can be solved by KKT condition, Cohen-Tucker conditions. It can be more easily solved if we look at the dual problem and solve that. And then the solution of the dual problem can be obtained by this system of linear equations. These alpha i's and b or B is the variable that one of the WB we want to find. And here WIs are replaced by alpha. These are dual variables. Solving this system of equations will give us the optimal solution of this problem. This can be rewritten in the form of system of linear equations like this. Alpha is the vector with components alpha I, and A matrix here is with elements Aij equal to net product of xi and xj. So solving this will give the solution of the dual problem, which we denote by alpha star and B star. From alpha star, we can get the optimal W star given by this equations. Once you obtain W star and B star, then the optimal classifier obtained from this is H star X is equal to sine inner product of W star X plus B star. Now, as we see here, we obtain this W star B star by solving this system of linear equations. But we have seen in last module that there is a quantum algorithm, HHL, which can solve a system of linear equations exponentially faster than any classical algorithm will do it. So therefore, to solve that, we use this HHL algorithm to get the solution and hence then get H star. This way you will get exponential speed up over the linear compared to the classical algorithms for this problem. We talked about the training sequence may not be linearly separable. So in that case, the optimization problem that we considered above can still be used. As we said, this is a more general situation where it can provide optimal solution even when the XIY are not linearly separable. However, it can happen the H star, the optimal solution obtained by that may not perform that well because there may be a lot of mixing of the two class data. In that case, nonlinear classifiers can, of course, do much better in general. But the problem is getting a good, proper nonlinear classifier, which will classify the training sequence properly and also perform well in general. So to address this problem of getting good nonlinear classifiers, which can be computationally obtained easily, we use the method of kernels, which is what we will explain below. To motivate this method, and we consider the following things. Suppose x1, y1 to xn, yn are the training sequence. Xi belong to Rn. And these are not necessarily nicely linearly separable. In other words, the SVM that we obtain above may not give a very good performance. In that case, what we do is we used a nonlinear mapping phi from Rm, from this domain, to Rm plus 1, where M1 dimension is much larger than M, and then consider the classification problem in this transform domain. For that, we consider phi xi, corresponding each xi, and take the corresponding label yi. We consider this data and try to linearly try to use SVM on this data. And since there's a much larger space, there is a good chance that the optimal algorithm for SVM in the transform domain may perform much better. Let's give an example for that. So consider this example. It is a simple example, two class problem. We call them class 1 and class 2. You could label them 1 and minus 1. There are two samples, 1, 1, minus 1, minus 1 in class 1. There are two samples, minus 1, 1, and 1 minus 1 in class 2. And we have plotted them here. This is x1, this is x2. Star, the cross is class 2, and the blue points are class 1. Now you can see very clearly that this data is not linearly separable. You try it yourself and try to find any linear hyperplane which will separate these properly. Now, on this, we apply a nonlinear mapping phi from R2 to a larger space Rx. X we are denoting by x1, x2. Then phi x in this is this mapping, giving this mapping x1 square, x2 square, square root of 2, x1, x2, square root of x1, square root of x2, 1. If we look at in this transform domain and consider just two components, the third component and the fourth component of this vector, and we plot them here. So these are the class 2 points and these are class 1 points, and you can see very clearly that these can be in this transform domain very easily linearly separated, let's say by this line. So therefore what we see is that if some data is not linearly separable in its original space, by taking some appropriate phi nonlinear mapping from that to a higher space, we can possibly classify them by linear maps in the transform domain. Now, back to the kernel methods by which we will try to do this. Kernel K is a mapping from Rm cross Rm to R, any mapping. If for any n positive integer and x size in Rm, any x size, n samples in Rm, we define kxi, kij is equal to inner product of xi, xj, and this way we define this matrix K with ijth element kij, we obtain an n cross n matrix. If for any n positive integer, any x size, n x size in Rm, we define for given k an n cross n matrix, and if it so happens that this matrix that we have defined is positive semi-definite symmetric matrix for all such n and all such x size, then kernel K is called positive semi-definite symmetric kernel. Examples of that, kxx prime is inner product of x prime plus c whole raised to power d. C is some positive constant and d is positive integer or some other constant as well. D will be this is called polynomial kernel and d is called the order of this. Another popular kernel is Gaussian kernel. Kxx prime is the exponential minus norm of x minus x prime square. Why it is called Gaussian kernel is because this is Gaussian function. So for these kind of positive semi-definite kernels, there is an important theorem available. So that is this: if K is symmetric positive semi-definite kernel, then there exists a Hilbert space H and a mapping phi can be nonlinear from Rm, the original space, to H, and this H and phi are such that Kxx prime is equal to inner product of phi x prime. So this is what we are going to exploit to get these nonlinear mapping phi starting with kernel, positive semi-definite kernels. Now we choose a symmetric positive semi-definite kernel, and we need to choose it carefully. Careful in the sense it depends on the application. And two common popular classes are the one that we have given above, that is the polynomial kernels and the Gaussian kernels. Corresponding to this K that we have chosen, we will from the above theorem get associated nonlinear mapping phi and H, the range space of this. Dimension of H in general will be much, much larger than the dimension of the domain of X, which is M. Now, in this transform domain, phi x1, y1, phi x and yn, we use SVM to obtain the optimal classifier. As we said, in general, especially if we have picked K carefully, this optimal SVM obtained now in the transform domain generally performs much better than that in the original space. Here is an example. But okay, so before that, let me just complete it. Once we have SVM, as before, we use the dual optimization problem and write this into this form. Now this A matrix has ijth element, which is inner product of phi xi, phi xj, because now we are working in the transform domain. So that is equal to above theorem kxi xj. So we define this system linear equation this way and solve that by HH algorithm. And this is how we can get optimal solution at a much faster rate in using the quantum algorithms. So an example of how this kernel method can help. This is again two-dimensional data. X1 is this, X2 is this, and now blues here are class 1 and reds are class 2. But if you look at it, this data is not linearly separable. We use kernel, polynomial kernel of order 3, where D is 3. And in the transform domain, X1 and X2, this data comes out like this. And so these are X1, X2, again same, but this gives the optimal classifier. So this classifier corresponds to one value of C. This may correspond to another value of C, and so on. As you can see, suppose you pick this and this, then within this is class 2, outside this is class 1, and we can see it does a fairly good job of good classification if we are picking this and this. It's not perfect in the sense it does not classify all the training data perfectly, but still the error loss is much less in this case. And of course, one can use other kernel methods to obtain even better methods. So this is just to illustrate how using kernel methods, non-separable, linearly separable data can be classified in a good way. So quantum speedup, as we mentioned earlier, for this kernel and SVM method, using HHL provides an exponential speedup over the classical algorithm that we have. In addition to that, we can get further speed up using another quantum algorithm. That is to compute K, Xi, Xj. Remember, for the kernel methods, this is what we use in the on the training data to get the linear system of equations. Now, we provide a quantum algorithm, which is called swap test, which can compute these quantities for certain kind of K. For example, in particular, many of the polynomial kernels, which will provide the classical speedup. So now we provide this quantum swap algorithm. This is the algorithm. Given two vectors, phi and psi, it computes norm of inner product of phi psi square. And this is computed via this algorithm exponentially faster than it can be done via the classical algorithms. And the quantum circuit to do that is this. Remember, this is Hadamard gate, and this is phi and psi, the two vectors, and this was the swap thing. Okay. So, and here you feed in 0. Using this circuit, you measure the first qubit. This is the qubit, and its output, we are going to do it using 0, 1, is either going to be 0 or 1, giving these two values. And probability of getting 0, which is P0, is equal to half plus half into norm of inner product of phi psi square. So if we can calculate this P naught, the probability of getting 0 at this observation, then from this we can get this quantity, and hence from that we can as well get this. Now, how to get this P naught? P naught can be computed by repeatedly doing measurements on the first qubit. So every time you start with this data and make measurement and find out how many times, let's say you repeat it for 100 times and you find out, let's say 40 times, it turns out to be 0, then P naught is approximated by 0.4. So this is how you get P naught, and from there, this quantity as well as this. This is exponential faster than the classical algorithms to compute inner product between two vectors. And importantly, this is independent of the dimension of the vector phi and psi. From this algorithm, we can also compute the difference of the norm between these vectors and take mod square. How we can do that is, you want to find this quantity. So compute this. This can be done classically, and you call it phi1, and then compute inner product square of that from the swap test that we have given above. And that's how you get this. So this quantity, computing this inner product, difference of the inner product norm, will be useful to us in later algorithms that we are going to be using. Thank you very much.